So we'll actually exercise this now in a little notebook. Let me see. If I put my participant window up, is that blocking your screen, or do you not see that?
Don't see it.
Okay, excellent. Good. Just blocking my screen then. So please go to the InSAR lab. I know that most of you are on, so that's pretty nice. I can actually spy on you. We have 86 servers running, so most of you should be ready to go. And so if you navigate to the Notebooks, SAR Training, English, UNAFCO, InSAR folder, the one that you started earlier today, in this folder you see a notebook that says UNAFCO, InSAR, Monday Homework 2. And if you all click on that, it will bring up the notebook. Veronica, we will take a break in maybe about 15-ish minutes. Is that okay? Yep, okay. So please all click on this notebook and start it up. And you should see a notebook that looks like this. And hopefully all of you are successfully opening that. If you have issues, raise your hand, please. And maybe Paul, you can follow, or somebody can look through. Mm-hmm. So this is sort of a notebook a little bit to get warmed up with the issue of modeling and sort of connecting the geodesy that comes from InSAR. So InSAR gives you geodetic information about the displacement of the surface. And putting that into geophysical information, which is sort of the parameters of the physical process that you're interested in. That's really, in the end, as a geophysicist, what you want to know. Oh, Ozzy, if you don't have the notebook, if any of you don't have the notebook, please go to Control Panel and stop your server, and then restart your server. You may have had your server run for quite some time before we push that notebook up. So if you don't have the notebook, stop your server and restart the server, and it will pull the notebook in. Awesome. So this is this little exercise will basically put into action some of the stuff that Gareth just described. We are looking at a volcanic event, specifically at a surface deformation or surface displacement at Okmok Volcano in Alaska. Okmok is a very nice site. It's a very agitated volcano. Not all volcanoes show strong deformation when magma moves around underneath the volcano, but Okmok is very pleasing for InSAR folks because it shows quite significant deformation whenever magma is moving around. So we'll look at Okmok Volcano, and we have surface displacement measurements, which in this case come from InSAR. And we use those to figure out the source model parameters for a Mogi source. So even though Gareth kind of dissed Mogi a little bit as sort of a simple model, and it is a simple model, but we use it partly because of simplicity of the model in this first notebook. And what we will do is we will not do a formal inversion of the forward model. We'll describe the forward model briefly, and Gareth's already done this, but we'll use a grid search method that I'll introduce here real quick, which is this brute force approach that I mentioned earlier. Is basically we try out a whole variety of different forward models and then pick the collection of parameters that fit our source the best, fit our data sets the best. Also, kind of a heads up, this contains a little bit of a homework. It's really to get you used to working within these Jupyter Notebook frameworks. It is a little small coding exercise in Python. Basically, what you have to do is use an existing function and modify it slightly to estimate something slightly different about the source. You'll see that the entire notebook comes really in 5 parts. We'll briefly run through the first 4 of those, and you can do most of this on your own. I'm going to show you real quick how to run the different steps. and talk you through this, but feel free to go all the way to step 4 on your own as I talk you through to save some time. And post questions here if you have any issues as you run through the notebook. You shouldn't have any, but you'll see that the main steps also show you a little bit of how these notebooks work. Notebooks are sequential Python code, so you should always run cells in a notebook in sequence, because you usually create parameters or load packages early on that you will need later on in the notebook. So we'll go through importing some of the relevant Python tools that we need for this. Then we'll talk a little bit about the event that we're looking at, and we download and visualize the data. We'll write some code or run through some code that sets up the forward model for Mogi, and then we solve for the inverse model using grid search. So please, if you click on this little arrow, it expands this first section of the notebook. And feel free to run through this. You can do this either by clicking this run button and run through the different cells, or if you like shortcuts, there's also shortcuts for all of this. If you're on a Windows machine, it's Shift-Enter to run a cell. If you don't know a shortcut that you would like to use, in the top menu bar, there's a little keyword symbol. Not sure if you see this. And this keyword symbol is going to tell you all the different shortcuts that are available for your operating system type. So feel free to use keyboard shortcuts as you wish. So in all these notebooks that you'll be running, in the first step, there's a few Python libraries that are being pulled in. In this case, we use one that's called OS, which allows you to do operating system calls out of the notebook. We use matplotlib, which is a very nice Python-based environment or package to create visualizations. If you've done MATLAB before, the matplotlib functions and plots look very similar to MATLAB. We use NumPy, which all of you may know. And we use some features that we wrote at ASF to make interacting with data sets a little bit easier, like and we load some functions from an ASF Python package in here as well. So please run through those two. So the first one imports the necessary libraries, and the second one just tells matplotlib that it should put figures in the notebook in a very specific way. If you have an error, run no module found GDAL, you may have not run. I don't know why I would need GDAL in the first place, but you may not have run all codes sequentially. So try this again to start from the beginning. So in the next section, it tells you a little bit about the event. So OCMOC, does deform quite heavily. This data set is pretty old nowadays. This is from the year around 2000. OCMOC has erupted several times over the last 20, 30 years. It's one of the more active volcanoes in Alaska, in the Alaska Aleutian chain. In that little figure, you see that it sits sort of halfway out the Aleutian chain, where the sort of Pacific plate dives under the American plate. Fairbanks, I sit all the way up here, and so OCMOC is constantly observed by the Alaska Volcano Observatory, because when it erupts, its ash cloud can obstruct or can interfere with airline traffic. Most of the airline traffic from the west coast of the United States to sort of the Asian countries like China and Japan actually crosses over the Aleutian chain and causes issues. So it's constantly observed. In this case, this volcano has GPS stations on it. These little dots show you GPS stations that are on the volcano. The blue ones are permanent stations, and the red ones are campaign stations that have been maintained in the past. So here we look at two SAR scenes. These are ERS2 C-band SAR data. one acquired in 2000 and one acquired in 2002 at around the same time of the year to preserve coherence. And it shows volcanic inflation in this case. You'll see it's an inflation of about 3 centimeters of the surface related to some magma movement under the surface. If you look at this figure to the right, you see these vectors which show you GPS measurements of the inflation. So on the east-west side, you see sort of a radial a deformation where stations move away from sort of a center point. The little star, here's the center point of the motion. And on the right-hand side, you see upward motion of these stations also. So it's like a radial upward deformation, which is typical for point-like volcanic sources that behave similarly to what's prescribed by a Mogi source, like a balloon-type inflation of the surface. So the first step then, as you go forward, is to download the data set. In this case, this is a prepared data set. So if you run these code cells in a row, it will first create a little folder on your environment where the data sets are being deposited. And then it grabs a data set from a storage space that we've created. This is an Amazon Web Services bucket. And so we grab this little data set and pull it into our environment. We'll define some variables. So the data set that is being grabbed has about 1,000 by 1,000 samples in lines and in sort of range and azimuth, if you want, at a 40-meter resolution. So every pixel covers about 40 by 40 meters on the ground. And this is a C-band wavelength. So one, and we'll talk about this later in the class, one phase cycle of a C-band data set measures about 2.8 centimeters of motion on the ground, of sort of range motion on the ground. And so one fringe, which is something that you'll learn about later in the class and you may have learned about before, covers 28.3 millimeters on the ground. So we read in the data set. We, in this case, convert the data sets to a displacement unit in centimeters unit. And in this case, this is ground displacement, where a positive measurement is motion toward the sensor. So mostly uplift, in this case, toward the sensor. So Gareth talked about this earlier, about line of sight motion and sort of ground motion. So this is provided in ground displacement, this data set. Okay, in the last step, we create a little mask. Because this is an island, there are lots of pixels in that scene that are decorrelated, and we mask those out so that we only are working with the data set that actually makes sense and actually has content. And at the last step, before we go into more detail, if you run these following notebook cells, it will create, first of all, a function, and then a little plot of this deformation data set. So did everybody get to this stage? The coherence threshold set here is 0.3. Let me know. Please raise your hand if you weren't able to create this plot. There's one hand. Maybe so I see one or two people with issues. Maybe what we can do is send a note on the Slack channel to me, and then in the break, I'm gonna work with you and find out what your issue was. Let's go with that to not delay it for now. And for now, you can follow along, and then in the break, I'm gonna solve your problem with you. Okay, So what you see here is on the left, actually, so this is still in line of sight displacement here on the left, where actually we have negative values here in the line of sight displacement because the range is getting shorter. Later on, we'll work in ground motion. And the displacement here is about 3 centimeters. So this down here is in units of millimeters. So it's about 3 to 3.5 centimeters of uplift. And because one fringe covers about 2.8 centimeters, when you look on the right-hand side, this is sort of a re-wrapped interferogram where one color cycle from blue to blue would correspond to about differential motion of 2.8 millimeters. We see that we have a little more than one fringe of motion here. You see there are holes in the map. These are places that were masked out. Most of those were masked out because of low coherence. So all of the water has very low coherence. You see there's a part in the middle of the crater that is masked out. This actually, as a side note, this was not decorrelated, but in this crater, we actually have an old lava flow that is deforming, and so it's contracting still because as it's cooling down, and it's deformation that's not related to the source underneath it. So we mask it out here to not bias the estimates we get for the source underneath. So sometimes you may have other deformation sources in your environment that you would like to probably remove before you actually estimate the source, to not mix two different kinds of deformation signals in your analysis. Okay, so now we will try to determine the source model parameters for this deformation. And we will be using a Mogi source as as the model of choice here because of its simplicity, and also because in the past the Mogi model has shown to be a good approximation for deformation at OCMOC. So the way OCMOC behaves can be reasonably well modeled using a Mogi source. So these next sections in section 3 are a little bit of an explanation of the Mogi model. First of all, it gives you again these the equations that Gareth already provided. Basically, the Mogi model prescribes or models a deformation on the surface, which is here denoted as U in this case. So you have a three-dimensional surface movement on the surface, and it prescribes it with a set of source parameters. It says that the way the surface deforms depends on, first of all, the three-dimensional location of the source. So the X and Y location on the sort of a two-dimensional surface location, and Z sub S, which is sort of the depth of the source. In addition to these three parameters, it also says that it depends on how much magma moved in or out of the source. So there's a volume change, V, that's also playing a role in how the surface deforms. So we see here the surface deformation depends on the X, Y, and Z coordinates of the source, as well as the volume change in that source. And so if volume change increases, then the surface deformation increases. And the way volume change causes surface deformation will also depend on this little parameter nu, which is the Poisson ratio. It sort of describes how rock reacts when you put it under stress. So basically how the stress is getting propagated to the surface. And as Gareth mentioned earlier, we assume that this Poisson ratio is constant without between the source and the surface, which is a very bold assumption that we're making here. So for every point on the surface X, Y, Z, we then can calculate the amount of deformation that occurs at this location. given certain source parameters x, y, z, and given a volume change parameter. As also Gareth mentioned, the three-dimensional surface deformation that we have, this is the surface deformation U. In the case of InSAR, we do not measure the three-dimensional surface deformation U directly. What we measure instead is a projection of this three-dimensional deformation vector into our line of sight. So the line of sight L here is pointed from the satellite down to the ground. And what we are measuring is the projection of the three-dimensional vector U into the line of sight. And so here are some of the projection equations that you can look through. But basically, it takes our deformation and calculates the component of the three-dimensional deformation that points into the look direction of the sensor. So that's the measurement that InSAR is collecting. If you were to have a GPS station instead, it would be able to measure all three components of U directly. So the next section in 3.3 provides a forward model for the Mogi source. So basically, this is coding up the forward model of a Mogi deformation, and it calculates a range change here for that Mogi source. So if you run that code, it sets up that function that we will run in the next code cells, and it basically takes the three-dimensional coordinates, which is the depth of the source, the northern and eastern coordinate, and the volume change, and converts it into a range change measurement. And so now that we so now we have the Mogi source model set up, we have another little function that we'll write, which allows us to create simulated displacement data based on Mogi source forward modeling. So we can now plug in the Mogi source parameters here, and it will spit us out a simulated interferogram or a simulated deformation map by running the Mogi forward model several times for different inputs. So once we have this, we can run a first experiment. So what we do here is we now plug in different sets of Mogi source parameters into the forward model and plot the deformation that this Mogi forward model is creating. And what we are doing here is we run different sets of forward models. And in this case, what we do is we keep the source depth constant. So we set the source depth in this case to a depth of 2.58 kilometers. We also fix the volume change to a certain value in cubic kilometers, but we vary the location of the source in certain steps. So we start out, these are relative coordinates, we start out with putting the source in the middle of our interferogram, and then we move it around by a few kilometers in X and Y and create different kinds of forward models. So if you look at those, what you see here is the forward model the forward model the deformation that the forward model is predicting. In range change, the star always indicates the XY location of the forward model that we picked. And you see if you change these XY coordinates, then where the deformation is going to be predicted is changing. You see it in different locations. So if you want, you can now play around. So there's a suggested exercise that you can do at home. You can change some of these forward model parameters. You can increase the depth, decrease the depth, change the volume change. So in your homework, I encourage you to just play a little bit with these source parameters and get a feeling for how the predicted deformation is changing as you change the source parameters. It gives you a little bit of a feeling for how the Mogi forward model works, and how the different parameters affect surface deformations you see on the surface. So please, in your spare time, you can run through that a little bit just to get a feeling for how the source reacts. And I give you a little bit of a code cell that you can run to go through that exercise. So as a last step so what you see here in these plots is that, if we have a given surface deformation, we can create simulated surface deformations, and you'll find that some of these simulated deformation products will look very similar to your observations, and other ones may not look very similar to your observation. And this already may give you a feeling for which of your model parameter settings may fit your observations better, and which of the model parameters may fit not as well. And we'll experiment with that here in a little bit. So if you go through section 4. So now we are trying to figure out which parameter combination of source X and Y coordinates, source depth, and volume change fit our data set the best. And if we assume that the model is a good description of the physical process, then these best fitting parameters are the most likely solution for your actual source depth and location and volume change. And so what we are trying to do, usually in an inverse model, we describe the best fitting set of source parameters as the one set that minimizes the misfit between the forward modeled or the predicted surface deformation and the actual observed surface deformation. So often we do that using the so-called methods of least squares, where we define the best set of model parameters as the one that minimizes the square of the differences between the forward model and the observations, the sum of the squares of the differences. So basically, in a simple way, what we can do is we can run the forward model GM many times, and for every output of that forward model, we can calculate the pixel by pixel difference to the observations. We then square these differences for all pixels and sum them up, and we get a number. And we will find in the end the forward model that we've simulated for which this difference or this so-called misfit is the smallest. And so that's what we will do. We will loop through a set of Mogi source parameters. We will calculate the forward model for each of these sets of forward parameters. Then also for each one of them, we'll calculate the misfit. And then at the very end, we'll find the combination that has the minimum misfit. And we'll elect that to be our best fitting set of source parameters. That is a very simple way, not very computationally efficient, but a straightforward and simple way of calculating the best fitting source. So in the first step of this, we'll experiment a little bit with misfit. And what we are doing here one more time is we are simulating different forward models, and we use the same set that we used before, in the sense that we keep the source depth constant, we keep the source volume change constant, but we vary the X and Y location of the source. And what we do is then we create all these different forward models for these different sets of parameters, and we'll calculate the misfit, in this case simply the difference between the predicted deformation and the actual measured deformation for these sets. So if you run through these code cells, so if you ran through this code cell, you get a set of plots, And hopefully you all got this set of plots. And what you're seeing in this set is the residual between the forward model that we calculated and the actual observation for these different combinations of XY coordinates, as well as the fixed source depth, which was fixed to 2.58 kilometers, and a fixed volume change. So what you see here is that for some of these solutions, like for this one specifically, where we put the source, the X coordinate at the 18 kilometer coordinate and the Y coordinate at 20 kilometers, we see that there is quite a bit of difference between the forward model and the observations. We have some positive differences over here where this red blob is showing, and we have some negative differences over here where the blue blob is showing. What this large difference shows us is that this set of source parameters are probably not the correct solution, because this set of source forward parameters doesn't seem to fit our data sets well. So if you look through these different solutions, you find that these top three don't look like they're a good fit. But if we get to the middle row, we get a little bit better. If you look at the middle row left solution, we'll see that there's less misfit or less difference already. And if you go to the center spot, we see that it's getting pretty close. For the center spot, most of the areas now are green, which means that the difference between the forward model and the observation is fairly small. There's some residual blue that we see here and some red, but it looks much better. So this is a much better set of source parameters than these other ones that we looked at before. And so this is in the end how inverse modeling works, is we try to find the set of source parameters that minimize the residual between observations and forward model. And we can automate this process. Instead of just looking at these different plots, we will now automate this process in the next code cell. And so what we're doing here is we run a so-called grid search, where we again fix the source depth and the volume change. In this case, we pretend that we know this information already. You don't necessarily have to fix this. You could do a four-dimensional search. We're fixing it here to make the process much faster. If you have to search through a four-dimensional space in small steps, it takes a very long time. It's not very computationally efficient. So in this case, we assume that we had some other information, maybe from seismic data or from GPS, where we think that we know what the source depth and the volume change was. So we fixed that to these two parameters, but we were uncertain about the exact location of the source. So we are now varying the source location in the X direction from 19 kilometers to 22.2 kilometers around a certain center value. And we changed that in 200-meter steps. And we also changed the Y coordinates in a certain range in 200-meter steps. And so for each of these steps, we now run the forward model by running this the Mogi source function that we created early on. And then we calculate the difference, the misfit between our observed measurements and our forward model predicted measurements. And this gives us a number for each of these simulations. And then at the very end, we pick the combination of XY values that gives us the minimum difference. So if you run this forward model, you will see that it goes through all of these iterations. And so it runs through these iterations, and it sort of tells you where it is. It runs 100, in this case, 176 simulations. And runs through those here step by step. So now we have done 66 of those, 77 of these forward simulations. And at the very end, once it's completed, it will spit out the XY coordinate combination that gave us the smallest misfit between the model and the observations. So we're almost there. There you go. So based on misfits, we find a source location of 20.6 kilometers in the x direction and 21.8 kilometers in the y direction. The accuracy of this here is limited, first of all, by the quality of the model that we are using. So we're assuming again that the Mogi source is a valid model for this event. And it is additionally limited by the step size we choose in this grid search. So in this case, our step size is 200 meters. So in reality, the best solution may somewhere be close to those two within a 200-meter step size. So now, once we found the best solution, we can plot and inspect the so-called misfit function. So please run this next code cell. What this is showing you is for every XY parameter combination, it shows you in a color-coded way the difference between the observations and the model. So for each combination, we can calculate one number which describes the misfit between those two, between the forward model and the observations. You see, if we are very far from the optimal solution is shown as a star. If you're far away from that, you get very large misfit. So these red pixels show you very large misfit. And in a well-behaved model, like in this case, you see how the misfit is continuously reducing as you are approaching the optimal solution. And so there are solvers out there like least square solvers, maximum descent solvers, and so on, that allow you to converge to that optimal solution quickly if you have a nonlinear problem based on the shape of your misfit function. But here you see that you get a gradual decrease, and you find the minimum solution here where the star is. You also see that the misfit function is kind of circular, which means it doesn't matter which way you walk away from the optimal solution. The way misfit increases is about the same in all directions. This is a good indication that the two variables that we are varying, so the easting direction and northing direction, in this case are reasonably linearly independent from each other. So there's independence between those two variables, and that shows up in a fairly circular misfit function. In your homework, I actually have to have you vary this search that you're doing up here. And instead of searching for the XY coordinates, I ask you to fix the XY coordinates and instead search over the depth of the source in the volume change. And if you do that successfully and you plot your misfit function, you will see that the misfit function is not circular for volume change and depth. And the reason for that is that there's a little bit of a trade-off between those. They are actually not fully linearly independent. And so there's a way of varying both source depth and volume change without increasing misfit very much. So this misfit function is going to be very elongated. You'll see that when you run through your homework exercise. So this misfit function plot is nice because it tells you a little bit about how well-defined your problem is, and it also makes sure that you actually found a good solution to your problem. You want your star to be in the minimum. So it's just a good way of double-checking your result. Now in the last step here, we can plot our best solution. And so what we are plotting here is a variety of different things. We are plotting the original displacement in the look direction. We are plotting the rewrapped original observation as a rewrapped interferogram. Then we plot the best fitting forward model deformation and also a rewrapped version of that forward model. And we already see, if you look at the simulated interferogram and the observed interferogram, that they are reasonably close. And the last line, oops, it shows this also to you without the mask. And if you run this last code, it also shows you the misfit spatially. So it shows you the misfit here in absolute deformation numbers, and it shows you the misfit as an interferogram. They, in this case, look the same because the misfit is fairly small. We see some residual misfit here, where we have red misfit on one side and blue misfit on the other side. The difference here is again because of that this little lava flow that is deforming that we didn't fully mask out. We also see a little bit misfit around the rim. That is something that we'll talk about later in the class. If you were to have a look at the DEM in the area, you see that misfit is larger in places where topography is higher, or for pixels that are more elevated. You see that around this rim, but you see this also in other places. In this case, this misfit is due to atmospheric effects, and that's something we'll talk about a little later today. Oh, did you, the chat, are you talking about this error here? Is that what you were talking about? This is not an error, it's just a warning. Python is great because it's a very rapidly developing language. So if there's something that isn't available in Python today, but you need, you can almost, count on it being available in a few weeks from now. So it's very dynamic. It's very exciting. One downside is, though, because it's constantly changing, that sometimes courses, the code is developing and you have to update some of these functions. This is just a warning that the way I'm calling a certain function will change in the near future. And it's basically telling me to update my code to make sure that future versions of Python will still do what I want it to do. Okay, so this is just a little exercise in running forward models for a simple Mogi source model, understanding how inverse modeling works and what misfit is, and that inverse modeling basically tries to minimize the misfit between the forward model and your actual observation. It reminds you a little bit that in the case of InSAR, the Mogi source actually initially calculates a three-dimensional surface deformation. But what InSAR is seeing is only the line of sight component of that. So we actually had to write a little function that projects our Mogi source model output, projects that into the line of sight. If you were instead to run this notebook with GPS data, you wouldn't have to do that. You could use the output of the Mogi source directly and compare it to GPS. And in this case, what we did is we assumed that the depth and the volume change was fixed, and that we calculated the X and Y coordinates. And in a little homework exercise, I would like you to make some very slight changes to the code. So I provide you the little code cell to change. And what I would like you to do later on today is make modifications where instead of fixing Z and volume change, I want you to fix the X and Y coordinates instead. And instead loop through depth and volume change here. And so you may have to make some moderate changes to this one Python code. And it will give you the best fitting depth and volume change variables. And you should also be able then to plot the misfit function. And so please try to do that in the homework. And once you are done with your notebook, then right-click on your browser window and print the notebook as a PDF and submit it online as you have already done for your pre-course work. Okay, Do you have any questions? If some people have still issues with the notebook, please chat me up on the Slack channel, and we can fix that offline. If you don't have Slack channel, that's fine. We can also talk during the office hours this afternoon.
So there was a question, Franz. You said that coherence threshold was 0.3, but where do you set that up? Where was that in the notebook? Because I couldn't find
this was not in the notebook. We basically, in the data package that we download, there's a mask file that is applied, I think. Let me actually check.
I think I answered that in the chat, actually. It's not in the notebook, but there's a cell 8. Well, it's 8 in my version.
So in this case, that's already applied.
Yeah.
I think Gareth is going to reiterate a little bit later on, that removing these pixels that can't be trusted is always good practice.
Right.
The mask creation's there in cell 10, right? Create a mask.
Yep. So for uploading your homework, I think Paul Rosen shared with you last week a Google Drive folder, and we can share that one more time today. And on there, you can create a folder with your last name and first name, or family name and given name, and then you can upload it there. And again, to print, the best result I get if you use the built-in print function in the browser. Just right-click at your browser window and go to print and print to PDF. Yeah, if you haven't received here somebody pasted it already. And, either email us or contact us on Slack, and we'll get that to you.